So I am very happy and honored to welcome today's speaker, Hiranya Peiris, who is a professor of astrophysics at University College London and co-director of the University College London Cosmoparticle initiative. And she's also a professor of physics at Stockholm University. Her research aims to test fundamental physics using large cosmological data sets, including the cosmic microwave background and galaxy surveys, combining observations, theoretical physics, and advanced statistical methods. Hiranya got her PhD from Princeton University in 2003. Then she was a Hubble Fellow at the University of Chicago, where I had the pleasure to meet her and work with her. And then moved back to Cambridge as a Halliday Fellow of the Science and Technology Facilities Council. She began a faculty position at University College London in 2009. She was elected Fellow of the American Physical Society and Vice President of the Royal Astronomical Society. She was also the director of the Oskar Klein Center for Cosmoparticle Physics in Stockholm from 2016 to 2022. Hiranya's work has been recognized through many awards. I'll just name a few here. So she has been awarded the Fred Hoyle Medal in 2018, the Goran Gustafsson Prize in Physics of the Royal Swedish Academy of Sciences in 2020, the Max Born Prize of the German Physical Society and the IOP, and the Eddington Medal of the Royal Astronomical Society in 2021. And her contributions to survey cosmology have also been recognized through a share of the Gruber Cosmology Prize and the Breakthrough Prize in Fundamental Physics, both awarded to the WMAP science team that she has been part of. On a personal note, I would like to add that Hiranya has mentored me and guided me through my very first project at University of Chicago when I was beginning graduate school, and she has been really a source of inspiration for me ever since. So today she will be telling us about prospects for understanding the physics of the universe. Welcome to the IAIFI, Hiranya.
Thank you very much for that lovely introduction. I'm really touched, Cora, and it's really lovely to see you, and I'm inspired by you too. Thanks very much for inviting me to give this talk. Shall I share my screen now?
Yes, please.
Okay. Let's see. Is that working?
Yes.
Okay. Well, it's a real privilege to talk to such a broad audience. I should start by saying I'm a physicist. I'm not a machine learner. I'm actually using machine learning in my work. So I'm going to talk to you about that. I'd like to tell you about the prospects for understanding the physics of the universe in the next decade. And I'll specifically focus on topics where I expect machine learning technologies to have a strong impact. So let's see if the slides work. Okay, so let me start with where astronomy is now. Astronomy is now in the era of surveys. Surveys are representative samples of the universe measured at different wavelengths, sampling different epochs in the history of the universe. And since recently, we are also now able to survey the universe through gravitational waves, not just electromagnetic radiation. And by measuring representative volumes of the universe, we can try to learn something about the origin and evolution of the universe as a whole and its underlying physics. Mapping large volumes of the static universe is now very well established, and mapping space-time volume through also using the time domain is just beginning. So it's useful to start with where we are after a couple of decades of the so-called era of precision cosmology. So in the past couple of decades, we've determined the basic form of a cosmological model that describes observations at a range of redshifts and timescales in the history of the universe and physical scales as well, and does it quite well. We have measured the age and the composition of the universe and found strong evidence, but not yet a smoking gun, for the quantum origin of cosmic structure. Measurements of the cosmic microwave background and supernova 1A cosmology play cornerstones of that achievement, which has been recognized by several Nobel Prizes by now. Currently, we are transitioning into an era where further progress can come through combining information from multiple cosmological probes, as well as the synergistic information from astroparticle physics and high energy physics as well. So it's worth noting that despite all of this progress, major theoretical questions about the origin and the composition of the universe remain unanswered. While we measured its parameters very precisely now, the standard cosmological model remains phenomenological. So what is the physical nature of dark matter and dark energy? We don't know the answer to those questions yet. The next decade will be dominated by an explosion of data from electromagnetic sky surveys, and in particular by surveys of the cosmic large-scale structure. So this cartoon tiles space and time with observational probes. You can see early times going to late times, large physical scales going to small physical scales. Up here, you can see the CMB, where much of the information in establishing the standard cosmological model has come from. And down here, you can see what's coming now and in the future, large-scale structure probes that span a whole range of times in the history of the universe and of physical scales. The probes overlap in time and scale and should help us piece together a self-consistent history of the universe. So the project that I'm personally investing most of my time on, and I'm very excited about, is the Vera C. Rubin Observatory's Legacy Survey of Space and Time, or LSST. LSST is one of the ultimate big data projects in astronomy. It's starting operations in a couple of years. The types of pictures of the universe I've discussed so far are static, they're frozen in time. Rubin will return to every patch of the sky, over half the sky, every 3 days or so, and do that for 10 years. And by stitching those images together, we will make a movie of the dynamic universe. This will enable us to study space and time in a way that's never been done before at this scale, and expand the surveyed space-time volume by a factor of about 1,000. LSST will enable diverse science missions at the same time. In addition to improving our understanding of dark matter and dark energy, in particular their physical nature, it'll make an inventory of the solar system, and it'll make this movie of the universe that I mentioned earlier, and it will also map the Milky Way. So it will measure 37 billion objects in space and time. That's 30 trillion measurements. That's about 60 petabytes of raw data over the course of the 10-year survey, and about 20 terabytes a night. And the data processed products will span about 500 megabytes at the end. Petabytes at the end. So this is very big data. It is not just big in volume. The rate is high, and the variety of the data is high. So it is really big data. Just to give you a sense of what I mean by this data deluge, up to 10 million alerts a night will be served within 60 seconds of detection of something changing on the night sky. So on every visit, Rubin's image will be differenced with respect to a template, and transient and variable sources will be detected, associated with metadata and previously known information, and pushed out to community alert brokers, where astronomers will be waiting to filter these events and find the ones of interest to them, and to trigger follow-up observations from other facilities and telescopes. This is an enormously challenging data mining problem, especially if you're after very rare sources like the precious electromagnetic counterparts of gravitational wave sources. Machine learning methods will have to do a lot of heavy lifting here. And we need to be ready for this data deluge in real time in just a few years' time. It's very exciting and just also slightly daunting at the same time. So in the coming decade, all of our cosmological probes will be dominated by systematic uncertainties. We need to transition from precision cosmology to accurate cosmology. It's no use just getting smaller and smaller error bars. We need to also converge onto the right place and find the right cosmology, and that's extremely challenging. Cosmology is an observational science. So a key question is how we compare theory and data in order to draw conclusions about fundamental physics. It's going to get much harder now. This is a challenge that the field has to grapple with now. And a key message of this talk is that cosmological interpretation is increasingly reliant on evaluating computationally costly, non-linear models with many parameters. So how do we address this challenge? This requires a transformation in our analysis technology. Much of my work in the last couple of years has been geared toward addressing this challenge, and in particular, investigating whether powerful machine learning techniques can be incorporated into a principled analysis framework to give robust and accurate inferences. I'll now talk about a few examples from my recent work, but at this point, it's worth noting that this is something that broadly impacts all aspects of observational cosmology now and in the future. So just taking a step back, what are machine learning models good at in astronomy? So classical machine learning techniques have been used very successfully in the field for decades for many applications. This includes making fast and flexible models for mapping between complex and very high dimensional data sets, particularly for classification, accurately speeding up forward modeling and data emulation, and many applications where physical models are simply not available or tractable. For example, anomaly detection or automated discovery in very large, very high dimensional data sets. So let's contrast what physical models are good at, good physical models. These are some characteristics of good physical models. They hopefully follow from explicitly enumerable sets of assumptions and physical principles. This leads to a mathematical model that can be solved to yield useful predictions. They can be deterministic or probabilistic. And they're explainable. They're rooted in cause-effect relationships that are grounded in domain knowledge. Hopefully they generalize beyond the initial domain in which they were constructed to explain a wider range of phenomena. They hopefully compress information. They explain a wide range of phenomena from a minimal set of ingredients. They're parsimonious in the sense of Occam's razor. And their domain of validity can be quantified explicitly. A typical exemplar is effective field theory. So how can we make machine learning models more like physical models in order to incorporate them in a trustworthy manner into our analysis frameworks? I think there are two common desiderata that we need to get to. One is interpretability. We need to account for why a machine learning system reaches a particular decision or prediction. And the second is explainability. We want to map this account onto existing knowledge in the relevant science domain. This is currently challenging because of the black box nature of many modern machine learning architectures. I should also point out that many physical models satisfy my list of desiderata, my list of characteristics only partially. For example, systems exhibiting emergent phenomena, it's very hard to sometimes tackle explainability in that context, and chaotic systems where predictivity can be quite challenging. So the first case study that I'm going to present is related to efficient emulation of computationally expensive cosmological simulations, directly addressing one of the challenges I raised earlier. This is work done in collaboration with these amazing people, including our fabulous host, Cora. A key unanswered question, as I mentioned earlier, is what is the nature of dark matter? There are many creative theoretical proposals, but there are two broad candidate theories, WIMPs and axions, that are particularly attractive because they solve major problems in particle physics, in addition to providing compelling dark matter candidates. Much of the experimental effort in the past has focused on the WIMP hypothesis, and it's only more recently that experimental attention is turning to axions. There's a huge part of the axion parameter space that's relatively unexplored. In particular, cosmological data can constrain light dark matter, including ultralight axions. The dark matter signal manifests as a suppression of power in matter fluctuations at small scales relative to the expectations from cold dark matter. And the strength of this signal increases as a function of redshift. For ultralight axions, the suppression scale is about a megaparsec, and that's set by the quantum pressure of the ultralight axions. When you look again at this cartoon tiling space and times, the scales sensitive to this power suppression relative to cold dark matter are these scales smaller than about a megaparsec. and the strength of the signal increases as a function of redshift. So looking at which scales and redshifts are spanned by these different probes, we immediately see that the Lyman alpha forest is likely to yield a good probe of this signal. So the Lyman alpha forest is the neutral hydrogen absorption seen in high redshift quasar spectra. It traces linear high redshift small scale density perturbations, and that makes it potentially a great probe for this power suppression signal. However, this can also potentially be mimicked by intergalactic medium astrophysics. Trying to separate out this gastrophysics from the fundamental dark matter signal can be a bit of a mud wrestling exercise. So one must marginalize over the intergalactic medium model to get dark matter constraints. Modeling the data sufficiently accurately to do that requires intensive hydrodynamical simulations. In this work, it was about 3,000 CPU hours per parameter combination in a 12-dimensional parameter space. That must be scanned very thoroughly in order to extract accurate constraints on the ultralight dark matter mass. So the key point is that one can't run a simulation at every point in a Markov chain Monte Carlo analysis to compare the model with the data and to infer the relevant parameters. So one needs to construct an emulator from a finite training sample of simulations. That can be as small as about 50. And we want to do that such that the modeling error from interpolating is small and quantifiable in parts of the parameter space which are observationally relevant. The key idea is to speed up forward modeling given this finite training set of simulations while maintaining accuracy in modeling the data so that a full MCMC analysis in a high dimensional parameter space becomes tractable. A corollary is that the subsequent analysis needs to propagate the modeling uncertainty as well as the theory uncertainty and the measurement uncertainty. I mention this because it's quite a novel setting in this field. In our work, we adopt Gaussian process techniques for emulating these high dimensional models. Roughly speaking, this is a smooth interpolation scheme that gives tight constraints where you have training data and broader constraints where there are fewer. Gaussian process emulation has actually been used in this field for quite some time now. The usual approach is to create a training set from a space-filling scheme, such as Latin hypercube sampling, which strongly suffers from the curse of dimensionality. So therefore, in any given part of the parameter space, you might have actually a very broad theory and modeling error. And if you happen to land from the data in that parameter space, actually a modeling uncertainty can dominate your error budget, and we don't want that. So the key idea we brought to this is to incorporate active learning of the training set via Bayesian optimization so that we can get the accuracy where we need it. So Bayesian optimization balances exploration, where the current emulated uncertainty is high, with exploitation, converging in areas of high posterior density. This is done through an iterative process. I'm going to now illustrate that quickly with a cartoon example. So here there's a toy 1D function that we're trying to emulate. This is the current iteration of the emulator and its uncertainty. We have training data over here. This is the likelihood. So this is the current emulated likelihood. And you can see there's a large modeling error here and the posterior density is high. And then you can use an acquisition function. In this work, we use the GPUCB acquisition function. And you want to draw the next training sample from here, balancing this modeling error with this high posterior density. So you draw it from there. And now we look at the next iteration of the emulator. You put the new training point here. So now it's looking much better, the emulated function. And now the likelihood is looking like this. And you balance again the current modeling error and the posterior density, and your next training point will be drawn from there, and so on. So you do that till you converge, and the convergence criteria should be set so that this modeling error is actually much smaller than the measurement uncertainty. So we can compare this active learning scheme with drawing training simulations from a space filling scheme, which is what's done naturally in the past. That's, for example, from a Latin hypercube sampling. So given that more dimensions brings the curse of dimensionality, training samples randomly drawn in such a space-filling manner does not give you the accuracy where you need it. So after an initial basic emulator has been constructed from a Latin hypercube sampling, Bayesian optimization then concentrates the new training points where extra accuracy is needed. And in this case, the parts of the parameter space which are observationally relevant. So in this particular case, the red constraints come from a Gaussian process modeling using the Latin hypercube simulations. You can see the error bars are quite large. And the blue constraints come from the Gaussian process modeling using the Bayesian optimized simulations. You can see the training samples from Latin hypercube sampling are wasted because they're not in parts of the parameter space where you want to get the accuracy. Because this iterative scheme allows you to beat down the modeling uncertainty relative to the measurement uncertainty, it also allows you to test the convergence of the simulator, the emulator. At some point, the posterior contours just stop changing. In this case, the red contours are from the Latin hypercube. They're clearly not converged after 30 simulations. And the blue contours are from the Bayesian optimization, and they're converged with only 26 simulations. So in this recent work, we used this approach to solve the challenging analysis task of constraining the ultralight axion mass from the Lyman alpha forest. This analysis improved the previous ultralight axion mass bound by an order of magnitude, and we were able to robustly disfavor the canonical 10 to the minus 22 to 10 to the minus 21 EV mass range for this model. So that's our constraint here. In our latest work, which is also with Cora, we considered light-dark matter with a velocity-independent cross-section, elastically interacting with hydrogen nuclei in the non-relativistic limit. This is a model-independent approach to setting dark matter models, but our results can be mapped on to specific models. So the dark matter proton coupling in the early universe strongly suppresses the growth of late-time small-scale structure, just like in the other case. And as you can see here on the left, the suppression scale is now a function of two parameters, not just one, the cross-section and the dark matter particle mass. So using our optimized emulator and high-resolution Lyman alpha data to look for this suppression, we were able to set the strongest limits to date on the dark matter proton velocity independent cross-section in the 10 keV to 100 GeV mass range. You can see our limit here. These limits are complementary to direct detection experiments and which have limited sensitivity to sub-GeV dark matter. So in these works, the interpretability and explainability is straightforwardly achieved because all that we are doing is essentially speeding up a computation. But in addition, we have a direct guarantee of the accuracy of the modeling with a quantification of the modeling uncertainty and an explicit quantification of the domain of validity of the emulator. So mimicking some of those nice characteristics of physical models. So now I'm going to discuss a more complicated scenario where explainability and interpretability is achieved through the use of machine learning to tackle otherwise intractable calculations in a Bayesian hierarchical model. This is work that has been done and is ongoing with a different set of amazing people. So huge galaxy surveys will yield many of the cosmological probes in this decade, as I mentioned. These surveys can be divided into two types: spectroscopic surveys, where you get a high signal to noise spectrum, and hence you get a precise redshift per galaxy. But these don't go as faint or as deep as photometric surveys, which yield broadband colors from which a photometric redshift has to be estimated. So these two survey types are complementary. And as you can see here, SLST is a photometric survey. This is an illustration to give intuition to those of you who are not astronomers. This shows a reference galaxy spectrum here and the filters of the Sloan Digital Sky Survey. And this is a key reference survey in cosmology. So photometric catalogs based on imaging surveys only get a handful of broadband fluxes from a handful of filters. That's going to be 6 for Rubin. And then we must estimate the redshift and its uncertainty from this much more compressed lossy information without access to the actual spectral lines. This is an animation, I'll play it in a second, showing what happens to these galaxies as the galaxy spectrum is redshifted to higher and higher redshifts. So hopefully that will play. And down here, you can see the fluxes from the Sloan bands as a function of redshift. We must infer the redshift using this lossy representation of the data, and doing so accurately is very challenging. However, doing this accurately is critical for getting accurate dark energy constraints from surveys such as SLST. This is the expectation for dark energy constraints after 1 year and after 10 years of the SLST survey. So we're going for really, really precise constraints, and we hope to make those also accurate. If these constraints on the dark energy parameters center on 0, that's a cosmological constant, and we're looking for deviations from 0 in order to work out whether dark energy is dynamical. And so the issue is that the accurate estimation of redshift distributions in tomographic redshift bins is absolutely critical to this enterprise. It is underlying many of the cosmological probes that were used to make forecasts for the previous plot. So if the estimated mean redshift of galaxies within a tomographic bin is biased, the cosmology will also be biased. For example, if you think your redshift distribution is this, and it is actually this other one, you will get a shifted and biased cosmology. So the higher redshift bins down there, where calibration spectroscopic data are more scarce, contribute much of the signal to noise for cosmological constraints, making the problem even more challenging. So spectroscopic training and calibration samples are generally not representative of photometric catalogs. They typically have a brighter flux limit, and the population of galaxies also evolves as a function of cosmic time. And they are heterogeneous, and they contain difficult to model selection effects. So this whole set of issues can introduce biases which are difficult to mitigate at the required precision for these next generation surveys. So a few years ago, we proposed a self-consistent hierarchical Bayesian framework using galaxy spectral energy distribution, or SED templates, to infer the redshifts for both individual galaxies and the redshift distribution of the populations as well. And this would then enable us to propagate the full uncertainty into the cosmological likelihoods. So while this principled approach provides explainability needed for robust cosmological conclusions, it has a critical limitation. So hierarchical Bayesian inference based on a selection of SED templates and simplistic population assumptions are inherently limited. These discrete templates do not characterize the full diversity of galaxy SEDs. What is needed is to replace these templates with accurate forward models of galaxy populations over cosmic time. And we've spent the last few years trying to crack this problem and develop such an approach. It is machine learning that is helping us crack this problem. So the key idea here is to use a high-dimensional Bayesian hierarchical model with machine-learned parts. The machine-learned parts basically take on heavy lifting related to computational challenges. One aspect that we are using is to use neural network emulation of population synthesis models, which are forward models describing realistic galaxy populations. So we want to replace the templates with those. And another aspect is to use flexible neural network parameterized probability density models, for example, normalizing flows, to describe population price and selection effects. These are really difficult to write down accurately with parametric forms, but flexible machine learning models can be calibrated to learn them. And these can then be slotted within a hierarchical Bayesian inference framework. So taking the first point first, so emulating stellar population synthesis, or SPS models. These actually are fast. They're not like the hydrodynamical simulations I discussed earlier. They can be less than a second. But the problem is that use cases require very large numbers of model evaluations. For example, a stage 4 galaxy survey catalog simulation would require about 10 to the 10 SPS evaluations. So Joel Lager's analysis of 60,000 galaxies under a 14-parameter SPS model, for example, this was back in 2019, cost about 1.5 million CPU hours. And here we're talking about hundreds of millions of galaxies for future surveys. However, it is fairly straightforward to generate large training sets of about 10 to the 5 samples, and that enables neural network emulators. So our first attempt at doing that was the so-called Speculator SPS emulator, which we published a couple of years ago. So here's an example of Speculator in action. So this is emulating DESI Bright Galaxy Survey SEDs. And the accuracy of that emulator was less than % over the 8-parameter FSPS population synthesis model for more than 99% of the SEDs. And at that time, generating 1 million SEDs took a couple of seconds on a GPU. And inference under SPS models can also make use of gradients, giving further speed ups as well. And this is the prior matching example that I was going to tell you about the normalizing flows. So basically, take, for example, a flexible function like the one being shown there, which is a double power law star formation history. It has a bunch of empirical parameters. Drawing from this model using a uniform prior on those parameters gives a good coverage of plausible star formation histories. They're sufficiently flexible to characterize star formation histories of many galaxies. However, if you draw uniformly from this prior, that gives a very specific and very bad prior on the current star formation rate. What you want is a more realistic target prior that encodes observations of more physical derived star formation history quantities. So this is a target prior, for example, that's a mass and redshift dependent prior that comes from Leger and Spiegel 2021. So what we want is to actually use that prior, but still be able to sample from this simple flexible model. Okay, so normalizing flows came to the rescue. So the solution was to train a normalizing flow to learn the implicit star formation rate prior, and then to divide it out to reweight the prior measure to match the target star formation rate prior, which is a function of mass and redshift. So this is the bad implicit star formation rate prior. This is the target prior. This is a function of mass and redshift. I'm just showing one example. And when you recalibrate, you can hit this, this star formation rate prior with the normalizing flows. That then induces a really peculiar looking prior on the parameters of the double power law model, but that's okay. I mean, those are just empirical parameters. So those are the types of ingredients that, from machine learning that are now encoded within the hierarchical Bayesian framework. So does it work? So these are exciting results that we obtained just a couple of weeks ago. They look very promising, but I want to caution that this is work in progress. What I'm showing here is not even yet using a hierarchical inference framework. It's just validating the population prior combined with observational selection. So the idea here is that if the model is any good, the simulated galaxy population, which encodes the galaxy evolution calibrated to observations, conditioned on the data model and the selection cuts, should be able to predict the redshift distribution of real redshift surveys. So in this slide, I'm showing a mock simulation of tomographic redshift distributions, which is part of an exercise we're doing to validate the approach. So here we take the gamma redshift survey, we make a mock simulation based on our population synthesis model, and we apply the flux and color cuts that were used to select the target galaxies for taking spectra for this particular survey. Then we make a tomographic selection in a couple of redshift bins based on photometric redshift estimation, as is done in real tomographic analysis. And we just simply plot the redshift distribution of the resulting mock catalog. We then compare these to the actual redshift distributions from gamma, already without any fitting or inference, just sampling from the population prior that has been calibrated with machine learning. The match is pretty good. So we are very encouraged by this. So watch this space. We hope that this will solve the redshift distribution challenge of the upcoming surveys. So far, the work I've showed you manifestly achieves explainability simply because either through Gaussian process or neural network emulation, they're basically speeding up otherwise intractable computational steps within Bayesian inference frameworks. The final example that I'm going to discuss is quite different. This is work done with yet another set of amazing people listed here. So before discussing this technique, I want to highlight a conceptual leap that we need to make in cosmology in the coming years to make best use of our rich data sets that we will be obtaining. So the process of structure formation takes small perturbations in the matter density at early times, and through gravitational instability evolves them into very nonlinear large-scale structure at late times. This is a process that we can simulate very well using cosmological hydrodynamical simulations. This is the shut up and calculate approach to cosmological structure formation. So an important point here is that we in principle know everything about this process. We know all the microphysics that goes into our simulations, and we can compute all the details of the end product of the simulations. However, it remains very challenging to answer cause and effect questions about the macroscopic structures that form within the simulations, even though we know all the microphysical ingredients that went into the simulation. It's like the difference between biochemistry and biology. And yet this is really critical to the future of cosmology if we want to extract the rich information within the cosmic web and to explore the increasingly overlapping interface between cosmology and galaxy evolution. So I want to pose here several questions in this context. Can we reliably access the rich information in the cosmic web and use it to stress test our understanding of cosmological physics, which largely derives, let me remind you, from modeling linear physics? Can we understand the mesoscale phenomena in structure formation? Can we cleanly answer questions like what aspects of the initial conditions and the environment determine the mass and the angular momentum and other properties of dark matter halos? Can we explain the close to universal phenomenology like dark matter halo profiles, the halo mass function, etc., that arise within cosmological simulations? So one approach that my collaborators and I have been developing is to use explainable machine learning architectures to try to disentangle cause-effect relationships in complex structure formation phenomena. So we wanted to use convolutional neural networks for this purpose for obvious reasons, really. They don't require any featureization. The CNN learns directly from raw data, and they're able to effectively learn highly complicated nonlinear mappings. But the disadvantage is that deep learning is basically black box. The features that it learns are encoded in very high dimensional models. So how do we extract physical knowledge from a deep learning algorithm? So how can we unlock the black box to gain physical insight into what the machine has learned? So the key idea here is to present a machine learning architecture called a supervised variational encoder. We made that up. It might be called something else in machine learning, with raw three-dimensional data, and to guide its training so that it learns to answer interesting questions about structure formation. So the key feature of this architecture is an informational bottleneck, which compresses the raw data into the information relevant for answering the question. So this is a low dimensional latent space. After doing this model compression, which is like a nonlinear version of principal component analysis, we can try to interpret what the model has learned as encapsulated within this low dimensional latent space. The first case study that we've applied this architecture to was to see if neural networks can discover the building blocks of dark matter halo profiles. So since the 1990s, we've known that dark matter halos exhibit self-similar universal profile shapes over 20 orders of magnitude in halo mass. Despite many attempts, the physical origin of this near universality is not yet understood. So modeling of profiles for a variety of purposes, both for determining the nature of dark matter, modified gravity, etc., and for galaxy evolution, relies on empirically found fitting formula. For example, the NFW and INASTO. And also there are other features in the outskirts of these dark matter halo profiles that relate to infalling material, and that depends on the dynamical history of the halo. So they're not able to be simplistically modeled using simple fitting functions. So these existing physical models based on empirical fitting functions actually lack explainability, even though we can compute these halo profiles very well with our simulations. So we trained an interpretable variational encoder to predict the density profile of a halo, given the 3D density surrounding the halo. So the network comprises of an encoder, which compresses the 3D input density into a lower dimensional latent representation. And the compression is done in such a way that the latent space only retains information required to predict the density profile of the halos. The second part of the network is the decoder that takes as inputs a random realization of the latent representation and a radius value, and outputs the spherically average density of the halo at that radius shell. So normally a variational autoencoder compresses the information needed to reconstruct the inputs. Here, the architecture is designed to compress and compartmentalize the information in the inputs needed to answer a question. So given a 3D density field, the network compresses the information needed to predict the spherically average density profile at a given radius when queried with that radius. So the decoder can be thought of as equivalent to an analytic fitting formula. The latter also takes in as inputs of halo-specific representation made up of 2 or 3 parameters and outputs the spherically average density at that given radius. So the encoder is equivalent to a parameter fitting procedure. It returns the halo's best fit parameters used by the analytic formula. But the inputs to the encoder and the fitting procedure are fundamentally different. The encoder extracts information directly from the 3D density field surrounding the halo, whereas prior to the fitting procedure, a clever human, via inspection of the data, using their physical intuition and understanding of the problem, has determined that spherically average density profiles exhibit a nearly uniform universal form, and proposed a functional form that captures this profile. So we're giving the neural network a very complicated problem, whereas a human has actually processed the data and built a model and then proposed an analytic formula for fitting to that model. So it's also worth noting that the classical NFW or INASTO fits are typically carried out using curated samples of relaxed halos. But we wanted to present the network with 3D data of a representative sample of halos in a mass range and see whether it learns a compressed model identifiably similar to the model that human intelligence has derived. Here I'm showing a couple of typical examples of density profile fits from the interpretable variational encoder, also showing the equivalent NFW fit for comparison. The interpretable variational encoder outputs a range of predicted density profiles given different random realizations of the latent representation. So that's what's leading to the error bar. We also trained an additional interpretable variational encoder to predict profiles further out than the radius to which typical NFW profiles are fit, to capture also this infalling of material in the outskirts of halos. So once this IVE has been trained, achieving interpretability is made possible if the latent space is disentangled. That means that independent factors of variation in the profiles are captured within different latents. Disentanglement is encouraged via a regularization term in the loss function and an independent Gaussian prior on the latent space. We check that the latent space is actually disentangled by measuring the mutual information between the latents. So mutual information is an informational theoretic measure that quantifies the amount of information in units such as bits or nats obtained about one random variable by observing another random variable. So in order to interpret what the machine learning model has learned, we compute again the mutual information between each latent variable and the distribution of ground truths for the density in each radial bin. So these three panels show the IVE models with 2, 3, and 4 latent dimensions. So what we're doing here is essentially like a nonlinear version of a principal component analysis, compressing the raw 3D information into information we care about. So the machine learning models have actually worked out there are 3 components or building blocks that make up the density profile. So you can see those here. 2D is not sufficient. 3D captures it. If you if you introduce a 4th one, it contains minimal information. So you can see that the machine has learned all the information that is needed to do this prediction. So here we are showing how the density profile predictions vary when you vary one latent at a time, holding the others fixed. So you can see that the machine learning model using this full 3D density field surrounding the halo as input basically discovers similar quantities to those used by the widely used NFW profile. So you can see that there's normalization of the profile captured here, the steepness of the profile captured there. And this one captures the outer component that contains information about the infalling material in the outer profiles of dark matter halos. And so it discovers the splashback boundary of halos while not knowing anything about the halo's dynamical history. So we found that very cool. So you can see also these points quantified by actually computing the mutual information between the latents and the NFW parameters, and do that for a sample of halos. So it's 2 of these latents, this one and this one, share substantial information with 2 of these 2 NFW parameters. By the way, the NFW parameters are correlated, they're not disentangled themselves. More broadly, the IVE architecture allows one to automatically generate a compact model captured within a disentangled latent representation that retains all of the information about the input data needed to predict a given property of interest. Mutual information then provides a principled quantitative interpretability measure to relate this compact representation to physical factors which underlie this mapping. So we will be working on applying these techniques to understand systems exhibiting emergent phenomena in structure formation and galaxy formation, where our ability to explain the phenomena is limited, despite knowing all of the microphysical inputs into the model and having numerical simulations which can precisely compute the outcomes. So this would represent a step towards machine helping humans discover new knowledge, construct new explanations through giving insights into their learning process. Lastly, I want to advertise my new European Research Council Advanced Grant project, which I'm hosting in Stockholm, where we are working on creative solutions grounded in explainable AI methods and applying those to analysis challenges posed by the coming Rubin data. If there are junior people on the call who are excited by what I presented, please come and work with me. So I'll end by just saying that there are powerful methods based and rooted in machine learning now available to enable cosmology with complex, costly models. This allows machines, in my view, to take on the drudgery of a complicated analysis like this, leaving humans to focus on the physics. Thanks very much again. I'm very happy to take any questions.
Thank you very much, Hiranya, for a very inspiring talk. I will ask everyone to unmute themselves to give a round of applause to Hiranya. And we take questions. So raise your virtual hand.
I have a non-virtual hand raised here at MIT. So thanks so much, Hiranya. In this last example, fundamentally you're doing kind of a parameterization task, but you have this variational piece in it. And I wanted to kind of understand the role of that variational piece. How much does this depend on the catalog that you're using for training? The fact that you're assuming kind of Gaussian prior in the latent space, does that matter or not? It seems to be essential to get this separation of the various factors, but I'm curious because I don't think I've seen a variational approach being used for that type of study.
Yes, so basically what we wanted to use the variational encoder part was to do the compression in the first place. I think that we can use any technique that leads to a compression that actually depends on the problem that you're solving. So in this case, it was a 3D CNN, and that was because we had 3D data to start with. If you have another problem which is represented in 2 dimensions or even 1 dimension, you probably can use a non-variational approach for the encoding. You just need to find some way to do the encoding that's appropriate to the problem, in my view. And what really matters here is actually achieving this disentangled representation, which is compressed, that you can interpret. So I believe that there could be different types of encoders that can be used in this context. In this case, no, it doesn't really depend on the training data. It relies on having a representative training set. We don't actually tell the encoder that halos have different scales. It works that out by itself, which is very remarkable. And it's actually able to predict the profiles for individual halos, not just stacked or average halos. One thing that we have done is to remove some of the detail of the profile by getting it to predict in alternate bins so that it's not so sensitive to a lot of tiny structures within the individual halo profile. So that's a sort of denoising, as it were, that we've done. But we don't have to do that. Also, in this case, we're using a problem where we know that spherically average profiles are actually important because we know that from the NFW analysis and so on. However, we can apply this to things that don't have that spherical symmetry, quantities that we might care about, triaxial properties of halos and so on, and also to look at substructure by not doing the spinning. So I think it's a very flexible approach. The key ideas are this compression, disentanglement, and then being able to use mutual information to measure information between the latents and what we care about, properties we care about.
Great. Thank you very much.
More questions for Hiranya? Yes, I see Sid, I think.
I have a quick question. Thank you for the nice talk. I'm curious how you actually do the disentanglement. Is it like a fully supervised disentanglement of the representation, or does it know something about like the R200 and concentration and so on?
No, it doesn't know anything about that. So we give it very minimal prior information. The disentanglement is actually achieved in this problem by a very simple encoder. It's basically a beta VAE. We first train it without any regularization so that we achieve the relevant level of predictivity. For us, that is set by being able to match the predictivity of NFW and ionosphere-type profiles. And after that, we sort of anneal towards a disentangled space by turning on the regularization term. And in the end, we achieve the mutual information between the latents to be about 10 to the minus 3 compared, so it's very, very small compared to the information that is contained in the latents. So actually doing quite simple things led to quite remarkable results in this work.
Yeah, okay. Data annealing. Thanks.
I wonder if, have you tried this technique, or it could be tried to different dark matter scenarios, different simulations with dark matter scenarios that you may be able to learn to discern those applying.
Absolutely. Yeah. So this was a kind of a first case study that we did to work out if this approach where you guide the encoding by getting it to answer a query, is that actually useful for compressing the information that we need? So now that we see that it works actually really remarkably well, it can be applied to many scenarios. It can apply to that one. We can use it to, for example, quantify the impact of baryonic physics, because these are just dark matter only simulations. We can try to work out what contrast what happens to a simulation which has baryons in versus not, and we can pull out those factors as well. Yeah, so there are many future projects and tasks that we're excited about doing. Yeah,
quite exciting.
Mm-hmm.
Are there other questions for Hiranya? Okay, I don't see hands. So if there are no more questions, let's thank Hiranya again for a very interesting talk.
Thank you very much for asking me to speak.
I hope to be able to see you in 3D.
That would be very nice. Thank you.